Test-Driven Development, Part 2. What is TDD? Hopefully in Part 1 I inspired you to want to learn more by showing you what is possible and how things could be, and that's why you're back for Part 2. Now you want to understand what test-driven development is all about. To understand test-driven development, you first need to understand unit testing. And you can't really do unit testing effectively without understanding how to use test doubles, like mocks. So in this video, I will explain unit testing, test-driven development, and test doubles. So what are unit tests? When we practice test-driven development, we create unit tests. But what are unit tests? So let's take a look at what unit testing is. Imagine this circle is the code of our software application. In an object-oriented programming language, our application is composed of objects. These objects have different responsibilities to do different things in our code. But they don't work in isolation. They call other objects to do things for them. They also depend on external resources like databases, services, and files to get things done. Because we're human, our application naturally has bugs all over the place. Some bugs are in our objects, while other bugs are in how these objects interact with other objects and how they interact with external resources. If the first time we test the software for a given release, we attempt to test the whole thing together, it could be really hard to troubleshoot defects this way. What we do to be more effective and efficient is isolate the objects and thoroughly test them in complete isolation from each other and from external dependencies. These objects are our units, and what we're doing here is unit testing. In this way, we first eliminate the defects from the units in our application. Once we eliminated the bugs from the units themselves, we are left with only the bugs in the integration. Now, when we integration test the whole app together, we can troubleshoot it more easily. When we encounter a bug, we can be more certain it is an integration issue and not a unit issue. So how does unit testing work? Let's take one of these classes in our application code. This class is what we want to test. In order to test it, we define a corresponding tester class. The sole purpose of the tester class is to test its one associated class in the application. As you can see, unit testing is very low level. When we unit test this class, it is isolated from its dependencies. What this means is when it tries to call other classes or use an external resource like a database, it thinks it is talking to the real dependency, but really, during unit testing, it is talking to a test double that pretends to be the real thing. A test double empowers our tester class to give the class we're testing the sense that it is running in production, when really it is isolated from everything around it in our development environment. For every new class we create in our software application, and every existing class we modify, we create a corresponding tester class. Let's take a closer look at the class we want to test and its corresponding tester class. The class we want to test has two parts. It has methods that are visible outside the class. Other classes interact with it by calling these methods. And it has methods hidden from the outside world that can only be called by other methods inside the class, not outside. The corresponding tester class is composed of unit tests whose sole purpose is to test the class we want to test. These unit tests are basically methods that call the visible methods of the class we want to test to make sure they work as expected. These unit test methods use the class we want to test in different ways to ensure the class we want to test works as expected under different usage scenarios. Note that the hidden methods are tested indirectly. If we want to test them directly, then we need to make them visible. Now that we have a general understanding of what unit tests are, let's talk about test-driven development. To this point, we talked about unit testing as a way to test our application code. We also mentioned that test-driven development is a very effective and sustainable way to do unit testing. Unit tests are an output of test-driven development. But guess what? Don't think of test-driven development as a way to test our production code. Think of it as a way to develop our production code. Test-driven development is a modern way to develop code. The code we develop is driven by tests. In fact, I rather say the code we develop is driven by our definition of correct behavior we write in the form of unit tests. Let's step through the process of test-driven development. Say we want to implement functionality to deposit money into a bank account. We decide we need a class called bank account that has a method called deposit. This method called deposit will take as input an amount of money and implement the functionality to deposit that money into that bank account. Guess what's the first thing we're not going to do? We're not going to start off by defining the class bank account and defining the method inside of it called deposit. No, that would be the traditional way of coding. With test-driven development, we have a better, modern way of coding. The first thing we would do is define a bank account test class outside of our application code. We would then think of a small aspect of the deposit functionality that we want to ensure works as expected. Say we want our deposit functionality to allow for deposits of very small amounts, like 1 penny. We define the deposit small unit test. This method attempts to deposit 1 penny into a bank account and validates it succeeds. We then run our deposit small unit test to see it fail. After all, if it doesn't fail, then we haven't defined new functionality, because it passes. Of course, at this point, in our case, it wouldn't even compile, because the bank account class it attempts to use is not even defined yet. So we now finally define the bank account class in our application code. You see, we didn't have to wait that long. This is what we're attempting to build. We're building it incrementally, the test-driven development way. Now inside of it, we define the deposit method, which is what we're focusing on building right now. We then write just enough code in the deposit method to pass the deposit small unit test. We then rerun our deposit small test and see it pass. Our deposit implementation now supports depositing 1 penny into a bank account. No more, no less. Yay, we now have 1 penny in a bank account. We move on to think of other aspects of the deposit functionality that we want to make sure work as expected. Who wants only a penny in their bank account? I want millions. Let's make sure we can deposit millions. Maybe one day we'll win the lottery. We decide to define the deposit big unit test to make sure our deposit implementation supports depositing very large amounts of money, like millions of dollars. We run the deposit big unit test and see it fail. Maybe because the variable we use to hold the dollar amount does not support such big numbers. So we now need to refine our implementation to support holding larger numbers. We write just enough code to make the deposit big unit test pass. We then rerun both of our unit tests. We run the deposit big unit test because we're working on getting it to pass. We run the deposit small unit test because if it fails, we now know we've broke something in the deposit method implementation and we can now fix it right away. Let's say in our scenario both unit tests pass. Wonderful! Now we move on to the next unit test. We think, what if a caller of the deposit method passes it a negative dollar amount to deposit? Nothing prevents a caller from doing that in our code. What does it even mean to deposit a negative amount? Is that something we want to allow? Should the deposit implementation throw an error? Should it treat it as a valid operation? Whatever the right behavior is, we want to make sure it works as expected. So we define the deposit negative unit test method to attempt to deposit a negative amount and ensure the deposit implementation behaves as expected when we do so. We run the deposit negative unit test to make sure it fails. Since we haven't implemented the corresponding functionality yet, it should fail. We then write just enough code in the deposit implementation to pass this unit test. We may need to add code or modify existing code to make it pass. We then rerun all the unit tests we have so far. We run the deposit negative unit test because we're working on getting it to pass. We run the other 2 unit tests to find out if we broke something so we can fix it right away. Let's say everything passes. So we just made 3 iterations of the test-driven development process in an attempt to implement the deposit method of the bank account class. Perhaps we reached the end of our workday. We incrementally implemented much of the deposit functionality and got to a point where all our unit tests pass. It is now a good time to commit this work in progress revision of our code to version control for safekeeping and continue to work on it tomorrow. That's what developing code the test-driven development way looks like. Now that we understand test-driven development a little better, let's talk about test doubles. Let's start with some context. Let's fast forward to what things will look like in the production environment once we release the software to our customers. Recall that the bank account class we built has a deposit method to handle deposits into the account. Let's say in production, the deposit method calls the fraud detection class to ensure the account we're depositing money into is not located in a sanctioned country before actually performing the deposit. And in turn, let's say the fraud detection class calls an external service to actually do the fraud detection work. As you can see, the bank account class does not work in isolation in the production environment. In fact, it probably depends on a whole bunch of other classes and external services to get its job done. But as you may recall, when we built and unit tested the bank account class in our development environment, we wanted to do it in complete isolation from its dependencies. Why? Because we may not have those dependencies available to us in our development environment. We may not have access to the fraud detection service in our development environment. Or the service may not even be implemented yet for us to use. Or accessing it from our development environment may just be too cumbersome. Also, while we incrementally build the bank account class, if every time we wanted to test our code changes, it runs all its buggy dependencies too, then it will make it so much harder for us to debug what we're actually focused on building right now and slow us down. So what do? How do we isolate the bank account class we want to build and test from its dependencies in our development environment? We use test doubles in our development environment. A test double looks like the real thing, but is not the real thing. The class we're building and testing thinks it is using the real dependency, but really it is using a test double that seems to behave like the real thing. Test doubles are quick and easy to implement. They don't actually do anything real. They just seem to do real things to the class we're building and testing. They're only used while we're building and testing that class. They're not used in production. So, for example, recall that our bank account test class contains a bunch of unit tests that define how the bank account class in our application code is supposed to behave and ensures it behaves that way. The bank account test class can tell the bank account class to use the test double instead of the real dependency while it's being built and tested. The bank account test class can also tell certain types of test doubles how to behave when the bank account class uses it. Keep in mind that test doubles don't actually do anything real. It just responds to its caller with a canned response, making it look like it actually did something real. In this way, we can isolate the class we're building from its dependencies and make sure it is defect-free before it is integration tested with its real dependencies later. There are different types of test doubles you can use. Which one we use depends on what we're interested in doing. A stub returns canned responses to its caller. It doesn't actually do anything real. It just responds with a hard-coded, predetermined response as if it did do something real. Stubs are simple classes implemented by hand. A tester class can tell the class it is testing to use the stub, but it cannot ask the stub after it was used how it was used to validate it was used correctly. We use a stub when we don't care how the stub was used by the class we're testing, because we're testing some other aspect. A mock also doesn't actually do anything real and returns fake responses. But unlike a stub whose responses are hard-coded ahead of time, a mock can be told dynamically by the tester class how to respond to the class being tested. After the class we're testing uses the mock, the tester class can ask the mock how it was used by the class we're testing. Mocks are created using a third-party library. Mocks are more popular than stubs because they're more sophisticated and easier to create. A spy is very different from a stub and a mock. A spy wraps a real class that does real work. It just spies on that real class that's doing real work. Later, the tester class can ask it how it was used. We use a spy when we can easily use the real dependency in the development environment, and we want to monitor how it was actually used by the class we're testing. Just keep in mind that defects in the real dependency we're using can drastically slow down our implementation of the class we're building, because we cannot be sure if a failed unit test was caused by a defect in the class we're building or a defect in one of its dependencies. A fake is kind of real, but a much smaller scale. It is a significantly smaller implementation of the real thing. An example of a fake is a slimmed-down database. Instead of using the real database service on large datasets on disk, we use a tiny database residing in memory. A dummy is used to simply pass in a junk argument to a method. It is an argument we don't care about for the particular unit test. It is an argument that does not matter for the particular test and does not affect it. And that's a wrap for this lesson. Let's do a quick recap before we say goodbye. We talked about unit tests, test-driven development, and test doubles. What did we learn about unit tests? We learned that unit test is code we write outside of our application code to define and validate how our application code should work. We learned that unit tests are a very low-level way of doing this, and that the developer writing the particular application code also writes the corresponding unit test code. What did we learn about test-driven development? We learned that test-driven development is a way to develop code, as opposed to a way to test code. It is a way of working that ensures we end up with a safety net of unit tests every time we touch our code. We learned it is an iterative process of first defining the expected behavior in a unit test, and then writing just enough code to pass it. What did we learn about test doubles? We learned that these units in our application code depend on each other and on external services and resources, and that in our development environment, these dependencies either prevent us or slow us down from validating these units work as expected. We learned that we need to use test doubles to enable us to test these units in isolation. Let's play a game to recap and learn some more. I'll ask you a question, take a moment to think about it, and then we'll answer it together. Okay, let's get started. When we talk about unit testing, what is this unit that we're testing? In an object-oriented language, the unit that we're testing is an object, more precisely, a class. We test each class in isolation from the other classes. We're testing the code inside the class. A class is of course composed of methods, also called functions. Really, we're testing these methods inside the class. In a procedural programming language, where there are no classes, we test these procedures, also known as functions. So how granular would you say this type of testing is? Is it high level or low level? It is very low level. It tests the behavior of individual methods in our code. Note that these methods we're testing could implement functionality defined by the acceptance criteria of the stories we're working on. So our unit tests could be determined from our acceptance criteria. But keep in mind that this is not always true. Some methods in our code that we unit test are generic, like a method to sort a list of items. For these methods, we need to define what correct behavior is as we code. What are unit tests made of? Are they a set of instructions for a person to follow or something else? Unit tests are made of code. It is peripheral software we write to test our production software. It is software that uses our production code in different ways to validate our production code behaves as expected under different circumstances and conditions. So if unit tests are software, then who writes them? Software developers write unit test code, not testers, not business analysts. But which developer writes the unit test code? A developer writing some production code functionality writes the corresponding unit test code for that functionality. Each developer writes the unit test code for their own production code, for their additions and changes. Other developers don't do it for them. Why? Well, let's take a look at the next question. When do we write unit tests? A developer writes unit tests as they code. A developer iteratively writes a unit test to define the intended application behavior, and then writes the production code to meet that definition, and repeats this over and over again. Where do we run our unit tests? We manually run unit tests locally in our development environment. Unit tests also run automatically by the CI/CD pipeline on every code commit to version control. Now, why test these units in isolation from their dependencies? Dependencies such as databases. For one, because in our development environment, these dependencies may not be available, are too slow to use, or too awkward to use. That database is simply not available or too cumbersome to use. But also, if we're focused on building and testing a particular unit, we don't want defects in units it depends on to slow us down and make it harder for us to debug. Also, by first removing defects from the units themselves, we can then more easily remove defects from the integration between these units. Okay, last one. Conceptually, what do unit tests create for us? What do they give us? Unit tests create a safety net to protect our code. Unit tests also act as the documentation of what the code does and how it should behave. A new developer can simply read the unit test to understand what the production code does and how it should behave. Great job, guys! Thank you for watching this video. I hope it was valuable to you. Please feel free to share it with others you work with to help them too. Also, feel free to explore our other videos to continue your own learning.